Hey guys, welcome. Can you guys hear me?
Yes.
Okay, I think I'll use a different laptop to log in from the conference site. Okay, let's get started. Hello, everyone. My name is Yi Chen. I'm from Amazon Prime Video. So we're organizing this generalizable HDR and SDR video quality measurement plan challenge together with PhD student Florin Chen from the University Texas Austin, Professor Imovic, and my colleague Henry here. So yeah, we have posted our survey paper of this challenge, include our results here in the globe. So I'll come back to that a little bit later. So we'll give you first 5 minutes beginning introduction, and then we'll let the participants present their solution, and then we'll come back to the final result analysis and the overall segment. So here is the question that reads so is FDR the type of disclosure from HDR? We all know, like, for video streaming application, we do the picture data that gives you a bit rate and resolution on actually plot. But the latter, we adjust the resolution and bit rate based on the level conditions the user is having. So another extra dimension that we should consider is the frame rate of the video and also the dynamic range. So, but both of them comes as a binary choice. For example, we have typically SFR standard frame rate at 30 FPS and 60 FPS. For example, for sports content. And for dynamic image, we typically just have a binary choice, SDR or HDR, although HDR have different formats. So do we need a metric that work well across different dynamic range? Since we're only delivering content in either HDR or SDR format, whenever we never mix them in a single streaming session, or we don't mix them when we reduce them when the user network experience network congestion, we don't integrate that from HDR to SDR. So we need a metric that works well. So this is the question that we have. So for this one challenge, we are creating an open source data set. This data set is based on the source data is based on this HDR data set. And we also put the archive link of the data set paper. You can take a look. This is how we did the select study. So here we're using 20 source content for training for this one challenge, and then 11 source content we preserve for testing as a private site. But this is special about this data set is that we're using this pairwise comparison with effective sampling protocol. So I will come back to this a little bit later after implementation, after the solution implementation, to tell you why we choose this. So and we also convert all the HDR source using connection to SDR. And encode it using that students will apply in SFM. So for each source, we have 18 TDS, including HDR and SDR resolution retrieved on the table here. And then we use 60 different to create this data set. And for the challenge, for this correlation, so very quickly, let's first see what the solution we have from the linear. So the first is
Can you hear us?
Hey guys, can you hear us now? Where's the echo actually? Using this mic. Hey guys, is there still happening? Can you talk, Baojun? Or are you not allowed to talk?
I start now.
Okay, you can start now.
Okay. Can you see my PPT?
No.
Wait a minute. Here,
Yeah, we can see it now. Yeah, you can start.
Go ahead.
Okay. Hello everyone. I am Baojun Li from the SLCV team. Today I am so happy to share our work, multimodal large language model for the video quality measurement. The datasets we introduced now, the training videos comprise a total of 300 videos. The testing videos include 198 videos. The most striking feature of the dataset is the vast resolution range. To achieve the SDR unified processing, we employed the FFM patch drive mobile tone mapping to convert SDR to SDR formats, followed by signal generations to a 1 lit display reference. Given the limited training dataset, which only have the 316 videos, we maximize the data efficiency through the adaptive sliding window with the cross-size equal 2/3 of the shortest video size. So we can achieve this sample expression while maintaining the spatial temporal coherence. Our approach leverages the multimodal large language model for the video quality measurements, built upon the individual 2.5 models. Our flavor employs the special window sampling to extract the local video patches, and then use them to train the model by rollup. During the inference, each separate patch is processed by the data model to get the quality score. and we can get the final quality score by averaging all the patches scores. We experiment the free individual 2.4 models, 1B, 2B, 4B models. We setting the LoRa length equal 16, alpha equal 48. Training the model use the fixed learning rate equal to E-4, beta size equal 24, with the different apples equal to 46. Finally, we use the special window sampling the M patches for per video, and then get the final quality score to by average stand. From the table, we can show that we average the apples patches regressions for the free individual 2.45 models. We can see that the 1B model all prefers the largest models in the all configurations. Besides, increasing the epochs from 2 to 4 boost performance. Besides, increasing the patches from 3 to 6 further improve performance. Besides, finally, using the regression to trade model not yet better results. So our final model setting is use the individual 2.5 1B model. LoRa length equal 16, alpha equal 48. Training the model use the learning rate equal to E4 and batch size equal 24 with the 4 apples. We also use the special window sampling to get the set patches and predict the quality score of them, and average them to get the final scores. In this approach, our method achieves the 0.4945 SRCC score and the 0.943 PLCC score in the test set. We can see that this approach outperforms the existing models. That's all. Thank you. Now, have any questions?
Okay, any questions from the audience? Can you guys hear us right now? Okay, I had a quick question, I think, Baojing, if you can answer. So I want to check, did you use any additional training data that's
No,
beside the training set?
Only the training data in the data set, not other data set, not other data.
So without the data enhancement, what kind of performance do you have? You mentioned there's a data augmentation, right? By sampling the spatial batch. Could you hear the question? So without the data augmentation, how much performance loss do you see?
How much?
Okay, I think we can catch up offline. Yeah, maybe we can pursue this next one. Okay, we get a question
What is the temporal sampling? Is it 1 FPS?
We sampled the video, only use the maybe 12 flavor, only the 16 or 12.
Okay. Thanks. Next one. So, Wei Sun, you can take over.
Can you hear me?
Wei Sun, are you here?
Can you hear me?
Yes. Yes.
Okay. Hi everyone. Today I will present our work titled Compressed VQA HDR Generalized for Reference and No Reference Quality Assessment Models for Compressed HDR Videos. This research is a collaborative effort between East China Normal University and Shanghai Jiao Tong University. In this book, we propose a unified framework designed to assess the visual quality of compressed HDR and SDR videos on both full reference and no reference scenarios. My name is Wei Sun. Let's begin with an introduction of our study. Video compression plays a fundamental role in modern video delivery. It's essential for saving storage space and reducing transmission bandwidth. However, compression leads to quality degradation, so it's important that this degradation can be properly measured and evaluated. On the right of this slide, you can see a simple comparison. We show SDR HDR content and HDR content after compression. As you can see, the compressed vision has clear quality loss. Compared to SDR, HDR content offers higher contrast and rich color depths, which makes such degradation even more noticeable and impactful to visual experience. Although video quality assessment have been extensively studied, most existing VQA models are trained and evaluated on SDR videos. This makes them less effective when applied to HDR content because HDR has very different visual characteristics, such as higher brightness, wide contrast, and rich textures, which are not well captured by models trained on SDR. This limitation highlights the need for more generalized models that can handle both SDR and HDR content effectively. The goal of our work is to build generalized full reference and no reference VQA models that can handle compressed videos across both HDR and SDR domains. However, there are two major challenges. The first is the limited availability of HDR training data. Most HDR VQA datasets are small in scale, typically just a few hundred videos, but the models usually require large scale and diverse data to run robust quality features. Without enough data, models are prone to overfitting and fail to generalize. The second challenge is the diversity of real-world video content. HDR videos differ significantly from SDR in terms of brightness, contrast, and bit depth. And beyond that, real videos vary widely in resolution, frame rate, and content type. This makes it difficult for a model trained on a specific domain to generalize across others. Addressing both challenges is crucial for building a practical and scalable VQA system. Therefore, we propose compressed VQHDR, a unified framework for evaluating compressed video quality on the both full reference and no reference setting. As shown in the figure, the full reference models takes both referenced and distorted frames as inputs, while the no-reference model only uses the distorted frames. To improve generalization, both models follow a two-stage training pipeline. For the full reference model, we first pre-train on a large-scale UGC SDR datasets, which provides diverse visual content, and then fine-tune on the HDR SDR VQA dataset for HDR-specific adaptation. For the no-reference model, we adopt an iterative mixed dataset training strategy, leaving multiple VQA datasets to improve robustness before fine-tuning on the same HDR SDR VQA dataset. Here's an overview of our model architecture, which includes separate branches for reference and no-reference setting. For the full reference model, both the referenced and the distorted video frames are passed through a shared swing transformer backbone, which produces hierarchical visual features at multiple stages. At each stage, we compute two types of deep similarity measurements, which are the texture similarity using global average statistics and the structural similarity using global variance statistics. Finally, all stage-wise similarity features are concatenated and poured into a compact representation, which is passed into an MLP for final quality prediction. For a no-reference model, we use the visual encoder of StickLip v2 to extract quality features from the distorted input frames. Instead of computing similarity that needs both referenced and distorted frames, we apply global average pooling on the last stage features to obtain a compact representation. Once the features are extracted, they are passed into a lightweight MLP to produce frame-level quality scores. Finally, to obtain the video-level prediction, we average the scores across all sampled frames. Before feeding videos into our models, we apply a pre-processing step to reduce computational cost. We use temporal sampling, extracting 1 frame per second, and spatial sampling resigns each frame to 384 using bicubic interpolation. This strategy preserves most of perception information while greatly reducing the pre-processing load. Then we introduce a training strategy. For the full reference model, we first perform pre-training on a large-scale UGC VQA dataset to learn diverse visual patterns. Then we fine-tune on the target HDR SDR VQA dataset, which enables effective transfer learning to HDR content. For a no-reference model, we adopt an iterative mixed dataset training strategy. Here, the model is trained jointly on multiple VQA datasets to help it learn generalized quality features. After that, we also fine-tune it on HDR SDR VQA dataset to adapt to HDR-specific distortions. We train and evaluate our models using 5 datasets. The HDR SDR VQA dataset is our main benchmark used for fine-tuning and validation. For pre-training, we use UGC VQA dataset for reference model and apply iterative mixed dataset training for the no-reference model using 4 datasets. The UGC VQA dataset, Waterloo LVC 4K datasets, ITM HDR VQA dataset, and live streaming datasets. We use 20% of HDR SDR VQA for validation and evaluate performance using SRCC, PLCC, KICC, and IMSE. This slide shows the performance of our full reference model compared to existing quality metrics. As we can see from the table, traditional methods like SSIM, DRI, STS, and VMAF achieves only moderate correlation scores. In contrast, our model achieves a much higher performance. This slide presents the performance of our no-reference model compared to existing no-reference VQA methods. We also observe that traditional metrics like NIQE perform poorly on the HDR content. Recent learning-based methods, science, minimalistic VQA, and Dover also show better performance, but still have limitations in generalization across diverse video types. Our model achieves consistently better performance across all metrics. This slide summarizes our performance on the challenge test set, where both full reference and no reference tracks are evaluated. In the full reference setting, our model outperforms PSNRY and VMAF, demonstrating better correlation with human opinion scores. In the no reference track, our model also achieves strong results of outperforming PSNRY. The scatter plots below visual confirm the effectiveness of our prediction. As you can see, our model's quality scores align closely with the subjective GOD values, indicating good consistency and generalization on HDR and SDR test content. We then present the application studies for the two tasks, aimed at understanding the impact of different backbones and training strategies. In the full reference model, we compare ResNet and SwingB. SwingB shows better performance even without pre-training, and with pre-training on the UGC dataset, it further improves across all metrics. For a no-reference model, we evaluate ResNet, SwingB, and SigLib V2. SigLib V2 clear performance best, especially when combined with our iterative mixed dataset training strategy. Compared to training on a single dataset, it significantly boosts performance. In summary, we propose compressed VQA HDR, a unified framework that supports both full reference and no reference quality assessment for compressed HDR videos. Our methods use advanced backbones like swing transformer and SigLib V2, along with effective training strategies such as pre-training and iterative mixed dataset training to significantly improve generalization across diverse video types. Through extensive experiments, we demonstrate that our models outperform existing state-of-the-art methods. As for future work, we aim to develop more generalized models targeting at high resolution, high frame rate, and high dynamic range video content. In addition, we plan to explore more unsupervised and self-supervised learning approaches to reduce reliance on expensive labeled VQA datasets and improve scalability. Thanks for listening. If you have any questions, please feel free to contact with the email.
Yeah, sorry, I think we have to not using the mic from the room so that to avoid echo. So any question for this one? Okay, in the interest of time, let's proceed to this next one. So Donia, yeah.
Can you see my slides? Can you hear me as well?
Yes.
Okay,
Yes.
perfect. Let me just start the timer so I don't exceed the time. Sorry about this. So hello, my name is Dunia Hamou. I'm a third year PhD student at the University of Cambridge under the supervision of Rafal Mansouk. And today we're presenting our new quality metric named Color Video VDP ML. So as you can guess for the name, it's an extension of Color Video VDP with the neural regressor for image and video quality prediction. So what is Color Video VDP? So Color Video VDP is a perceptual quality metric based on psychophysical model of the human visual system to assess the visible differences between a test video and a reference video, which can be shown either as a distortion map, as a histogram, or as a quality score. Because Color Video VDP is based on psychophysical models, it can natively account for SDR and HDR content, for the display specification and viewing condition. Furthermore, it is a white box model based on low-level vision, which allow it with very few learnable parameters, which allow it to generalize well across a diverse range of distortion. However, while it's based on low-level human vision, it does not really account for high-level vision. So let's take this as an example. So this is like the heat map we get for Color Video VDP for this video. And Color Video VDP assigns similar weights across the frame. So as you can see here, it's assigning similar importance to the foreground and to the background. And in reality, most observers are just focusing on the distortion on the foreground and ignoring what's happening or discarding the distortion in the background. Another problematic case of Color Video VDP is that it penalizes per pixel differences in high entropy texture, for example, the curly hair of this woman. And in most cases, again, observers tend to discard the small texture differences. So here in this work, we're trying to leverage the characteristic of Color Video VDP from the fact that it's generalizable, it accounts for SDR and HDR content, and it accounts also for display and viewing condition, and we employ a neural regressor for high-level visual processing, for example, saliency and texture similarity. So this is the framework of our Color Video VDP ML, and in this presentation, I'm going to delve into each block of our framework. So let's start with our backbone, which is Color Video VDP. So as any full reference quality metric is accepted as an input, a test, and a reference video. One main block that really distinguishes Color Video VDP from other metrics is its display model. So Color Video VDP operates directly on the physical units of the display. So basically, using the display model, or the physical unit of the luminance. So using the display model, it can transfer our input to exactly the light that is emitted from the display, taking into consideration the luminance of the display, the ambient light in the room, as well if the display is SDR or HDR. So in more detail, it's actually going to decompose our, or like transfer our input to the decal color space. So we have the luminance, again, exactly the light emitted from the display, and this was let it really account for display condition, as well for natively account for SDR and HDR content. It also transform our image to the red, green, yellow, violet channels, which are the chromatic channels, which allow it to account as well for chromatic distortion. It also employs temporal decomposition, and we get the transient channel, which kind of contain information about force motion, which doesn't really exist on this video, but that is what allows it to account for like temporal distortion. Color Video VDP then apply multi-scale decomposition. In particular, it apply the Laplacian pyramid, and this step allows to decompose our input into multiple bands at multiple spatial frequency, and this is necessary to able to like code contrast and apply contrast sensitivity function to get basically our test contrast and reference contrast in perceptual units. And this step is not only happening to the luminance, but it's happening to all channels. So it's happening to the luminance, red, green, yellow, violet, and transient channel. Then Color Video VDP apply contrast masking, which allow us to get exactly the perceptual difference across each channel and each band. Color Video VDP is usually, well, Color Video VDP in principle only take the perceptual difference and pull it to a quality score. However, here we're not taking only perceptual difference as features, but we're also taking the test contrast and reference contrast. And these features provide us information about the high-level visual processing. So again, from Color Video VDP, we're able to get for each frame and each channel the different band of test contrast, reference contrast, and perceptual difference. So this is an example of the perceptual difference kind of features. And if you imagine this information across all videos, it's gigantic information across terabytes. So to reduce the size, we decide to use like patch extraction. So across all bands, we take similar, like the same size patch. We take no overlapping patch of exactly the number of pixels per visual degree. And this information, we take it from our viewing condition. Then for each patch, we calculate the mean and the standard deviation. So basically two statistics, and reduce the information in a patch to only do these two statistics. So at the end, for each patch and for each band at each frame, we're going to have 24 features. So we're going to have two statistics, the mean and standard deviation for the 4 channels. And so we're going to have 8 features for the test contrast, for the reference contrast, for the perceptual difference, and we're going to have 24 features in total for each patch. And this step not only help us to reduce the size of our extracted features, but it will make our training of our neuroregressor more efficient. So for our neuroregressor, we wanted to learn kind of high-level visual processing, such as saliency and texture similarity. So here we experimented with 2 different networks, with MLPs and with transformer. So let's start with our saliency-based regression network, or we call it color video DPMS saliency. So the idea behind this network is to use 2 MLP predictors, one for distortion and one for the saliency. So the distortion predictor is going to take the perceptual difference features. So again, this is the features for only one patch, and is going to predict a score that represents the amount of distortion for that specific patch. The saliency predictor, on the other hand, is taking the reference contrast and test contrast features and going to predict a score that represents how salient is this patch. And this score is going to weigh the result of the distortion predictor. And then we're going to have a score per patch, per band and frame, which we're going to average all of them to get a final quality score per video. It should be noted also that our saliency predictor is not explicitly trained on like saliency ground-truth data. What we're doing is that we're training both our predictors on like quality dataset, and we want our saliency predictor to learn the saliency information in an implicit way. However, one big issue with this network is that it's going to take a single patch feature as an input. So if you imagine that we have one salient patch, you can imagine the patch next to it is probably also salient. But this kind of network architecture cannot learn this kind of relationship between the different patches. Hence, we also decide to like use transformer. And here we present our color video DP ML transformer. So we're using like the basic architecture of a transformer. So we're going to use the difference features for all patches, and we're going to give it to a patch encoding. So because our features already have meaningful information in meaningful units, so we employ simple linear layer. And then the encoded patches plus a learnable token CLC is going to be inputted to our transformer encoder, and the results are going to be given to an MLP to get a quality score at the end for each band and each frame. And then all of the score are going to be averaged across them to get a quality score for the video. One thing that you can notice here, for example, is that we don't have like positional embedding. It's something that we actually tried and gave us slightly worse results. We're also not learning attention across bands and frames just because of the complexity of the task. And we also know that information across band is similar and the units across them are similar. So we thought it may not bring much information at the end. So both of our networks, so color video DPM and saliency and transformer, was trained on 4 different datasets. So we're training on the HDR dataset, UPIC dataset, Love HDR dataset, and the XR dataset. So the fact that we are able to train on multiple datasets allow us our metric to generalize well on SDR and HDR content for images and video, and on multiple type of distortion like streaming distortion, image distortion, and display distortion. And this was only possible because all of these datasets were scaled in the GOD units, which allow us to provide like consistent quality across the different datasets. Plus, we also are testing our dataset on 8 like validation datasets, and this will allow us to like track in our monitor training, select the checkpoint, and also prevent overfitting. So let's start by looking at the metric performance. So here I'm starting by comparing the color video DP and the color video DP MS saliency and transformer, and we're comparing them to the test set from the challenge because we did like an 80-20 split. So as you can see, color video DP is doing pretty poorly, and that's because most like the dataset contains a lot of salient objects, and color video DP is just assigning similar importance to the background and foreground, so it's not doing well. On the other hand, both our color video ML transformer and saliency are drastically improving the performance, and you can see we have higher correlation to compare to color video DP. So to look at the comparison between color video DP transformer and saliency compared to color video DP, here we're showing all our validation sets, datasets, and you can see that not only color VDP ML transformer and saliency are doing better than color VDP on the challenge dataset, but also on UPIC. On other datasets like Alive HDR and XR David, so these are datasets that color VDP already do so well in them, you can see that the color VDP ML saliency and transformer is doing similarly as well. Color VDP ML saliency though kind of overfits and doesn't do so well, for example, on live mobile dataset, which is dataset that contain a lot of streaming or like transmission distortion. So because of the architecture nature or like the network kind of nature, it cannot generalize as well as color VDP ML transformer. But in general, we can see that our color VDP ML transformer is either doing similarly or drastically better than color VDP. Here we're showing the comparison between color VDP ML transformer and other metrics. So we actually tried multiple metrics, but here we're showing the most interesting results. So we compare it to Topic. So Topic is a quality metric that also uses transformer architecture. And you can kind of see that it does so well on the challenge datasets. However, it kind of doesn't do so well on ARM validation datasets. So example, it's overfitting on live AQA. It doesn't do so well on XR David. So in general, color VDP ML transform is doing slightly better. Similarly, or like way better compared to the Topic datasets. VMAF, on another hand, is a known quality metric that generalizes well on like streaming distortion. However, for similar reason to color VDP, because it's assigned similar importance to background and foreground, it's actually not doing so well on the challenge datasets. Also because it's specialized only on streaming distortion, so it doesn't do well on use display distortion like XR David. And this is one big benefit we get from training our color VDP ML transformer on multiple training datasets, is that it allows our like dataset to like generalize well to any kind of distortion. LPIPS, on the other hand, is like a very known quality metric, but in general, it's actually not performing that well on most validation datasets, especially the challenge datasets. So in summary, we can see that our proposed metric surpass or do similarly to like existing state-of-the-art metric on all validation datasets. To assess better the effectiveness of our metric in learning saliency and texture similarity information, here we're going to show the heat maps or the distortion visibility heat map. So we're starting by looking at color VDP ML without test and reference contrast features. So basically imagine just having a distortion predictor. So similarly to the main issue of color VDP, we are assigning similar importance to the background and foreground. Color VDP ML saliency, on the other hand, is doing slightly better, but still is given still a lot of importance to the background. Color VDP ML transformer basically mitigates from this issue, and you can see that it's focusing mostly on the foreground and discarding the distortion on the background. It's also not really penalizing the per pixel like texture per pixel differences in the texture. So in conclusion, in this work, we introduced color VDP ML. So this work kind of shows that the psychophysical model of the human vision can be combined with machine learning model. This allows us to improve the ability to generalize, account for different like SDR and HDR content, and for the display and viewing condition. And this ML head is enable us to train on difficult data sets and to learn high-level vision phenomena like saliency and texture similarity. We also were able to find that being able to train on large number of data sets will allow our metric to generalize better to distortion, and that was only possible because all of them were scaled in the GOD units. So that is all from my side. Thank you very much.
Thank you, Dunya. Sorry, I moved outside to avoid echo. So any question for Dunya? Okay, so we have one online. How are CI computed around S-Rock? What does it tell here? Is the code of the model available to test?
So we're going to make the code available. So we put already the link of the code in the paper, and we're just like cleaning the code, and we're going to make it available to everyone to use as well. So what was the first question? I didn't hear it well.
How are confidence interval computed around S-Rock?
Oh, so the confidence, well, maybe I can show this. So here we didn't look really do Busabi. We did something simple, is that we basically kind of assume that the standard deviation of the standard deviation, I think, of each score is basically kind of like 1, I think. And then we just like from that we try to get like the confidence intervals. but we didn't do it properly with bootstrapping. So that was kind of an estimation on how the interval like will look like, because we didn't exactly have the subjective score or distribution for our for like the scores that we got from the challenge data set.
map, not help or even hurt improvement of metrics.
So Yunjin, I think
It's a question about the savings features if you have with a model.
Sorry, I couldn't hear the question.
Hello?
Hello? Yeah, sorry, I couldn't hear the question.
Yeah, my question is about the savings map. So we savings map with all the time, all the content dependent.
can transcribe. You can type on the chat. Yeah. So the question is whether the synergy map can improve the model performance all the time,
So
or is
basically,
content dependent?
so this idea of saliency.
Yeah.
So basically, the idea is that if, for example, if you have a video that doesn't really obviously have a salient object or anything like that, so it's going to return to the previous thing, that it's going to give like similar importance across all the frame, and that will give us like similar performance to the color video DP, which was the case for like live HDR and XR David datasets, because they don't have really silent objects. But for datasets which have like a lot of human like or moving around or like the obvious silent object, the metric will be able to learn better. So the idea is that if there is not really any silent object, it will still do similarly to before, so it will not like the performance will not decrease. But if we have more silent object, the performance will increase.
I can add on that question. So like when you're training the saliency map module, did you use any eye gazing data?
So
Or some
now,
open data set?
no, we didn't train it. So we didn't explicitly train it on a specific dataset. We just like trained both predictor on quality dataset, and we wanted to learn in an implicit manner.
I see. Okay, that's very interesting. Okay, any more questions on this one? Okay, let's continue to the next one. In the interest of time.
Yeah, should I stop sharing?
Yeah, you can stop sharing. So, Amrisa?
Yeah. Let me quickly share my screen. I hope you guys are able to see my screen.
Yes, we can.
So, yeah. Good afternoon, everyone. My name is Amrita Premkumar, and I'm excited to present our work on learning video quality using lightweight, interpretable model built on handcrafted features and XGBoost regression. This is a collaborative project with Prajit Rajendran from University's Paris-Saclay and Vignesh V. Menon from Fraunhofer HHI. Here's what we'll be covering in this talk. First, we'll start with the motivation behind this work and define the problem we are solving, how to perform real-time video quality assessment without heavy computation. Then we'll briefly highlight some related work, including traditional metrics like PSNR and deep learning-based approaches. and where they fall short. Next, we'll present our system architecture, a lightweight and modular pipeline that extracts features and predicts quality using XGBoost. After that, I'll explain our information theoretic framing, where we interpret quality in terms of mutual information between the original and distorted videos. Then we'll dig into the feature design, the 7D VCA features, how we compute residuals, and how we construct the final fused vector. I'll follow that with our evaluation setup, including the data set, train and test splits, and model tuning. Then I'll show you our results and comparing against standard metrics and highlighting performance gains and interpretability. Finally, I'll wrap up with some conclusions and key takeaways. So online video is growing exponentially. Think YouTube, Netflix, live sports. But here's the catch. Measuring video quality still relies on old school metrics like PSNR or heavy neural networks that demand expensive hardware. We need a better way, something that's fast, explainable, and doesn't break the cloud budget. That's where our method steps in. Let's look at the landscape. Full reference models like VMAF are accurate, but you need the whole reference video and a lot of compute. Think turtle speed. Reduced reference methods are lightweight, but often outdated. No reference deep models powerful, but they need GPUs and gigabytes of training. Our method hits the sweet spot. Partial reference, low compute, interpretable, and fast, without needing AI wizardry. Here's our end-to-end pipeline. We start with just the reference and distorted videos. We extract handcrafted complexity features using video complexity analyzer, apply temporal pooling to capture average behavior, and compute residuals to estimate distortion. Then we add SSIM, a perceptual metric, to capture structural loss. All this is fused and passed into a lightweight XGBoost regressor that outputs a final predicted quality score, fast, interpretable, and reliable. We look at video quality through the lens of information theory. Think about video encoder as a noisy channel. What matters is how much information from the reference survives through to the output. Residuals capture what's lost. SSIM captures structure that's retained. Together, they serve as lightweight approximations of mutual information. And that's exactly what we feed into our regressor. We extract 70 features per frame using VCA. These include texture, energy, and chroma stats. Averaging them over time gives us a clean summary for both the original and the distorted video. The residual tells us what's lost, while SSIM tells us what's retained. Combine them and we get an 8D feature vector, compact, meaningful, and ideal for lightweight regression. We evaluated our model on a rich, diverse data set from the VQA Grand Challenge, 31 high-quality source videos split into HDR and SDR variants, made our test and train sets. Using just partial reference features, we trained an XGBoost model. Hyperparameters were fine-tuned using Optuna. The result, a balanced, efficient model that works across content types. Our model achieves a PLCC of 0.787 and SROCC of 0.832, outperforming a PSNR and approaching VMAF, but with only a fraction of the compute. Feature importance analysis using a SHAP reveals that the residual energy in the Y channel is the most predictive, aligning well with our mutual information framing. So most importantly, our method is 3 times faster than VMAF and fully CPU friendly, making it ideal for edge and real-time deployment. While our method is lightweight and interpretable, it does have limitations. So it's not a blind model. You still need some reference side data. Also, since we rely on handcrafted features, we may miss on complex or high-level video degradations that deep models can learn. Still, for many real-world applications, this trade-off is worth it. To wrap up, our method proves that you don't need deep networks or heavy computation to predict video quality effectively. By combining handcrafted features with a fast XGBoost regressor, we strike the right balance between accuracy, interpretability, and speed. So it's a practical solution for quality estimation in real world. So thank you so much for your attention. We are all happy to answer any questions or dive deeper into any part of the model or results. If you would like to follow up after the session, feel free to reach out to us directly via email. Our contact information is on the slide. Looking forward to your feedback and discussion. Thank you so much.
Thank you, Amrita. Yeah, we love lightweight metric. So we have a question from Andres. What is the complexity compared to low complexity, like the string-based metric like P04 family? And the HDR video tone mapped SDR before you calculate the metric?
So we haven't checked that actually. And
Yeah,
for
actually,
the question
yeah,
where HDR videos tone mapped first. So yes, we have done that.
okay. Yeah, actually, for the first part, we have some runtime data that I will share. So we can see the runtime speed compared to other metrics. Any more questions in this one? Okay, let me continue my presentation. So I need to rejoin because. So coming back to the analysis, so the motivation that we built, we have this grand challenge, is to have a metric that can channelize for both HDR and SDR. And the question we were asking is, when we cross compare HDR and SDR and treat a tone mapped video as the same content, how does a metric perform? So we have to choose a protocol that compare HDR and SDR. So hence we choose the pairwise comparison. And the active sampling is one of the methods that reduce the time required to run pairwise comparison, because full pairwise comparison is very costly. So this is also a work that we use called SAP, that's from Professor Mantuk's group from Cambridge. This protocol also help us, better measure the crossover accuracy. Basically, you get a resolution bitrate crossover on an uphill plot, and this protocol will allow you to choose a point to focus more on the point where you have more ambiguity, where near the crossover point. And we can also cross compare HDR and SDR. It's kind of like the yellow score that people get. So you can extend your subjective study. After you finish your first session, you can add additional different type of distortion to expand your data sets. And so we built this data set that compare HDR and SDR. So what we found is within content, when we compare within a single content, TSNR have a very good correlation and even crossover accuracy. I think we will have a talk on crossover accuracy tomorrow. But when we compare cross content, WMF is doing great, but TSNR is very bad. And for when we cross content, but include frame rate to the picture, WMF does not do a very good job. But some bitstream-based metric, because they have higher abstraction of the temporal space, like motion vector-related features, so that doing better when you add frame rate. So here in this work, we're trying to extend that to SDR and HDR. We found that no metric is performing very good when we jointly rating HDR and SDR. So here's an example. Actually, in this competition, we only treat HDR and SDR as separate content. So on the left, you have this GOD score that's recovered by using different anchor video for HDR and SDR. So that means even though the content is the same, but the tone mapped SDR version has its own reference. So when we compute 4 reference metrics, SDR has a reference and the HDR has its own separate reference. So in this case, all the metrics can achieve very good performance, 0.9 something. And when we jointly rating HDR and SDR, okay. Screen is shut. Can you guys see my slides? Okay, yeah, some people can see, I think. Yeah, I think we can see from the conference side. So I think it should be a personal issue. Okay, so coming back to when we compare them, when we read HDR and SDR in the same session, basically, so people will see both HDR and sometimes it compared with SDR videos, and people will see, okay, HDR probably is better at the similar rate. As you can see, for example, on the very top, on the very right of the screen, all the EQ and quality metrics say, oh, okay, the video quality is very high, near 100 at 4K. But people comparing SDR versus HDR will say, okay, HDR is better. So a lot of metric fails in this sense. And for FR metrics, many metrics doesn't even support, because the pixel format is different, doesn't even support comparing, taking both HDR and SDR as input. So this is the final result actually for this grand challenge. We are using the top one that HDR and SDR was treated as separate source content. You can see that everyone get from 0.8 above baseline to 0.9. But when we come to treating HDR and SDR as the same content, you can see all the correlation drops due to the issue I just mentioned. So I think this is an open question that we want the community to try to explore a little bit more. In the interest of time, we have posted all the final result on this slide and also in this archive survey paper. A few point that was mentioned is that the first metric, from Baojin, the SLVC that adapt the LVM fine-tuning using LoRa for video quality test, actually is a no reference metric that achieved the best performance here. And on the GPU instance, L40S, NVIDIA GPU, the performance is average runtime per video is 42 seconds. And it also worth mentioning that the last presentation we have, the Phoenix video, based on the VCA lightweight feature, only use CPU, even though the correlation is not the highest, but the runtime is very fast, only 10 seconds. That's basically real time because every video we have around 10 seconds. And for the transformer-based model, we have FR, multiple FR submission and NR as well. Those runtime are also listed here from 17 seconds to around 76 seconds. And the baseline we have here, P1204, because of the open source implementation, take only one thread. So actually decoding a 4K video took quite some time. It's actually the slowest, but there are room to optimize, make it multi-threading. And on the encoders, on the EQM metric, we actually kind of, there was some optimization work going into this implementation. So performance is around 16 seconds here with a 12 thread. And the VMAP for reference metric takes about 83 seconds. And finally, I think it's our award ceremony. I'll give it to Hai Wei, that's our principal scientist from Amazon Prime Video, to announce the winner. Also the prize.
Thank you.
All the organizers, if you ever hosted a conference or a workshop, it's a non-trivial effort. A lot of moving parts, and yeah, it's take a village really to host a workshop like this. And lastly, but not least, we definitely would like to thank the sponsorship of Prime Video Science, and especially our senior principal engineer Yongjun Wu. He has been the main driver to provide actually all the fundings for the cash prize, for this grand challenge. Yeah, with that, as we mentioned, we have 2 tracks: no reference track and full reference track. And based on all the correlation performance, you've seen that for no reference track, we have the first prize is given to the team from Baojun Li. You saw the multimodal LM approach really not only outperform all other non-reference models, but even outperforms the full reference models, state-of-the-art full reference model, which is very intriguing and exciting new area to further research and develop into. And the second prize for the no reference track is to the team led by Wei Su. And yeah, congratulations. And we have, for full reference track, we have actually 3 winners. The first prize goes to also a team led by Wei Su. I think, yeah, so they did a good job having a model, a work for the full reference as well. And second prize goes to the University of Cambridge team led by Donia, and congratulations. Yeah, and the third prize, yeah, goes to the team led by Amrita. I would dare to pronounce the last name here, but yeah, congratulations. And as she mentioned, their model provide a good trade-off between the performance and also runtime complexity. All that may not be the top performer in terms of correlation, but for certain use cases, the low complexity is a big plus. And yeah, so that's all the winners for our grand challenge today. And unfortunately, most of the teams, they cannot come here and be in person. And but we will email all the team the actual digital certificate and also follow up with ways to distribute the cash prize. So with that, yeah, this conclude our grand challenge. And thank you very much for your time, and enjoy the rest of your conference. Thank you.
And one last thing is that we have a quick grand challenge. If you can go to the next slides for the room. Yeah, thanks. So this is a learned image compression grand challenge that will happen at PCS later this year. If you have work planned, feel free to take a look at this grand challenge. So we're also helping running the infrastructure and the benchmark there. the price, there are also cash price, and the submission will open till end of August. And you can have also, if you have a lightweight model, can submit to CPU track, and GPU track is also available. Please check the website. Thanks for attending. I think we can conclude.